Hello everyone, welcome again to the second part of chemistry lecture. This time we're going to discuss about the different types of atomic theory. I'd like to start with Dalton atomic theory. There are so many theories before Dalton, but the Dalton theory is considered to be very much accepted by the scientific community. Reasoning from a large number of observation, Dalton made about 4 theories. The very interesting thing I would like to say about Dalton is that Dalton initially he was not a chemist. Dalton was an English teacher who taught English in high school. However, Dalton had so many interests about movement of molecules, particles, how the weather changes, what is the origin of hurricane. All these things would made him very passionate and interested about chemistry. And one of the things that a very amazing story about Dalton was that he lived in the 18th century, and during his time he didn't have any of the instruments like we have today. There's no any IBM technology or spectrometer that he can observe the movement of particles or atoms. He did everything in his basement, and he made 4 theories which is accepted by the scientific community. His first theory was that all matter is composed of indivisible atoms. Okay, matter is composed of indivisible atoms. An atom is an extremely smallest particle of matter that retains its identity during any chemical reaction. So that's one of his theory. The second theory is that each atom of a given kind having the same properties. Each atom of a given kind has same properties. So what it means is actually that each atom of a given element has the same properties. In other words, mass is one of such property. In other words, let's say for example, mass of carbon is not equal to mass of hydrogen, or mass of sodium is not the same as mass of oxygen. So mass would be considered as one of the property in this case. The third property, that's relative number, of any 2 kinds of atoms in a compound occur in small ratios. This is also another important theory of Dalton, and this actually will briefly define the difference between a mixture and a compound. As you noticed in our previous presentation, we discussed that one of the differences between a mixture and a compound is that a mixture has a variable composition, and at the same time a mixture can be separated physically, whereas a compound has a definite ratio, definite composition, and cannot be separated physically. So when Dalton says the relative numbers of any 2 kinds of atom in a compound occur in a small ratio, this law can be deduced as the law of constant composition. Say for example, water is a compound. What makes us think that water is a compound? Because water has always a definite proportion. Regardless of the sources, water can be composed from 2 atoms of hydrogen and 1 atom of oxygen. That makes water as a compound. So when we think about that, this will take us to something called the law of constant composition, which means the relative number and the kinds of atoms are always be constant regardless of the source. His fourth theory of Dalton is that atoms are not created or destroyed. This is basically known as the law of conservation of mass. In other words, if you have a chemical reaction, during a chemical reaction, whatever mass you have before the reaction is equals to the total mass after the reaction. Nothing has been destroyed or eliminated or disappeared. And the third theory can be deduced as the law of constant composition, like I said earlier, that the relative kind and number of atoms are always constant for a given compound. So, although Dalton has postulated that atoms were indivisible particles, experiments conducted around the beginning of the present century in our time showed that atoms themselves, they consist of subatomic particles like protons and neutrons and electrons. However, before we summarize the current model of atomic structure, I would like briefly consider as a few of a landmark of the discoveries of the latest model. In this textbook, we're going to discuss about Schrödinger equation. Erwin Schrödinger was one of he's an Austrian scientist. Erwin Schrödinger is the person that explains very well about the discovery of the subatomic particles. He was an Austrian scientist, and one of the things about Erwin Schrödinger, actually he used the model of Dalton atomic theory. However, Schrödinger uses the latest technology, and he also incorporated physics, chemistry, and mathematics, a higher level of mathematics, derivation and integration, to identify the or to address the subatomic particles and the electrons. And many scientists have found that Schrödinger equation of addressing the electron is the best explanation for the scientific community. However, don't forget that the foundation was laid by Dalton. So, in order to understand the Erwin Schrödinger equation, I would like to start with radioactivity or radiation. I would like to give you what's a radioactivity first. Where does radioactivity comes from? Radioactivity is actually a spontaneous emission of radiation. It's emission of radiation that comes from unstable nuclei. Okay, it comes from unstable nuclei. So, nuclei. Now, nuclei, when I say nuclei is a plural form of nucleus. So you have inside the nucleus of an atom, you have protons and neutrons. So there will be like a big collisions of protons and neutrons inside the nucleus of an atom. So this collision will cause instability, and by removing some energy in the form of radiation, the unstable nuclei will become stable. So there is this radiation, what we call it radioactivity. The energy that is released from unstable nuclei. That's called radiation, and this radiation can have different forms. It can be alpha radiation, it can be a beta radiation, and it also can be a gamma radiation. Okay, the reason why we need to explain the different types of radiation would help us to understand Erwin-Schrödinger equation in our next lecture, and then that will very well explain about the subatomic particles, the location, how we can address, and what would be their property as well. So let's consider the first radiation, which is the alpha particles. What is the characteristics of alpha particles? The alpha particles has a sign of the alpha sign. It contains two protons and 2 neutrons and has a mass number of 4. So the alpha particle is pretty much similar to the helium nucleus because it has a mass number of 4. The only difference between alpha particles and helium versus alpha is helium has protons and electrons, but alpha has only protons. Alpha is a positively charged particle. That's very important to remember. Alpha has a positively charged particle, doesn't contain electrons. Typical source of alpha particles is radium-226 is considered as one of the typical source of alpha particles. Sometimes isotopes of radium can be written as this way, or in some literature you may say the isotopes of any element can be written as the name of the element will be written, and then you will have the atomic number on the bottom and you will have the mass number on the top. So these two are same way that they can indicate isotopes. And what's an isotope? Isotope is atoms having the same number of proton, however they have different number of neutrons, because that's what we call it, isotopes. Different number of neutrons. So one of the isotopes of radium can be considered as the source of the alpha radiation. So the next radiation is considered to be as beta particles. It's absolutely different than the alpha particles. Beta have their own symbol like this. They have high energy of electrons. High energy of electrons, and they have a charge of -1. A charge of -1, and the mass number is considered as 0. They don't have a mass number. That's the main difference between the alpha and the beta radiation. The beta radiation actually produced from the unstable nuclei. What's happening inside the nuclei is that when the neutrons changes into protons, so we can get the beta radiation. The nuclear equation for the beta particles, I can just give you a little bit idea on that. If you have a neutron here with 1 and with the atomic number 0, and it changes, the proton changes into the neutron changes into a protons. Sometimes a proton can be designated as an hydrogen, because hydrogen also has 1 atomic number, and there's a radiation here which is identified as E with a mass number of 0 and a charge of -1. This is a kind of nuclear equation that's happening inside the nucleus of an atom. This is how a beta particles is originated or generated. Okay, so you can see the difference between the alpha and the beta radiation, and I'm going to also explain about the gamma radiation. Okay, well, the next one is the gamma particles. Gamma particles, it's written as gamma. They are high energy of radiation. They are similar to X-rays. No mass or charge associated with the gamma particles. They can be travel a great distance through the air, and they can be extremely hazardous. So shielding or lead or some kind of thick concrete is needed. You can easily protect the alpha radiation and the beta radiation using even lab jackets. They don't travel a great distance, they don't harm you that much unless they are concentrated. But the alpha particles need a special type of lead or thick concrete. So these are the three different types of radiations that I would like to discuss. To summarize these, all this radiation, the alpha, the beta, and the gamma particles, they originated from unstable nuclei. It is an energy, it's a radioactivity that is spontaneously emitted from the unstable nuclei, and once the energy is released, the unstable nuclei become a stable nuclei. And the reason why we need to learn about the behavior of the alpha, the beta, and the gamma, they are a very good way of explanation about the where the atoms, the subatomic particles, are located, especially when you discussed about the gold foil experiments by Ernest Rutherford. Ernest Rutherford is, I believe, he's a Swedish scientist, and he used the different types of radiations and their characteristics to address the protons, the neutrons, and the electrons. And his experiment, known as a gold foil experiment. And Rutherford, what he did was he used a source of alpha particles and he placed at the mouth of a circular detector, and his goal was the alpha particles to shot through the piece of gold foil. And what he discovered was most of the alpha particles went straight through the foil without any deflection, and some of the alpha particles were deflected at high angles. And one of the things that she identified was that those alpha particles that hit the center, they deflected, and some of them they passed without any deflection. And this gives him an idea that at the center there's like a dense positively charged region, and all the other part is like, he called it as a vacuum, because the alpha particles can pass without any problem, but some of them they are deflected. So at the center there must be some kind of dense region, a very dense region, which he said that that's a nucleus with a positively charged radiation. And he knows that alpha is also a positively charged radiation. So if alpha hits the positively charged radiation, there is no any way that can able to penetrate, rather they can be deflected. So the center is a positively charged nucleus, and the other part is like a vacuum. A vacuum means that there's nothing there, but the idea is that there are electrons, but as you know, electrons are always in move, so they cannot able to stop the alpha radiation. So that gives us a structure of the atomic model, that in the center you always have a dense region, which is protons and nucleus, and around the center there are like electrons. Electrons are located. So this is like an approval, or this is like a deduction from the gold foil experiments done by Rutherford. And he uses types of radiation to explain this. So after they discovered about where the nucleus and the subatomic particles, there were so many interesting experiments have been done about the radius of the subatomic particles, the nucleus, and the diameter. And they said that the diameter of the subatomic particles, the nucleus, would be like it goes to 1 to 5 angstroms. Now, angstroms is one of the SI units which is used to measure subatomic particles. It's a very smaller unit. It's like 10 to the power of minus 10 meter. So there are about these days about 118 elements are known, and the smallest one is going to be hydrogen, and then the biggest one is uranium. So uranium has the largest dimensions, maybe like 5 angstroms, and hydrogen will have 1 angstroms. So the range between most of the atoms is lie between 1 to 5 angstroms. And we also discussed about about isotopes. I already defined what anisotopes are, the atomic numbers. In some literature, you see the atomic numbers represented as a letter Z. Mass number is represented as a letter A. So isotopes, like I say, is these are atoms having the same number of protons and different number of neutrons. So I can give you an example. Say if you have carbon 612, carbon 613, carbon 614. The number on the top is always called as mass number. The number in the bottom, the 6, is called the atomic number. The atomic number, which is called Z sometimes. And the number of neutrons is always, you can subtract the mass number. By the way, the mass number can be represented as a letter A. So the number of neutrons would be like A minus Z. So that gives you the mass number. So in this case, the number of neutrons would be 6. Here the number of neutrons would be 7. Here's the number of neutrons would be 8. Okay. So one of the things that also we need to notice here, the number of protons and the number of electrons are the same if you have a neutral atom. That's one of the definition of a neutral atom. A neutral atom means that if you have the number of protons equals to the number of electrons, we call that neutral atom. If you have a charged ions, that's a different story. A charged ions, it don't necessarily have protons, and electrons are not the same. So that's very important to identify charged ions versus neutral atoms. The number of electrons is going to be exceeding or less depending on the nature of the atoms. In terms of metals, electrons always lose, then the number of electrons are always less. Whereas in terms of non-metals, electrons gaining, so the electrons will be greater than protons. So that's how you differentiate a neutral atom from charged ions. So, like I say, mass number is a number of protons plus a number of neutrons, but there is also atomic weights that needs to be explained here. Atomic weight is different than a mass number. Atomic weight is the weight of average mass of all the isotopes of the elements. So that's what we call it. Atomic weight. Atomic weight and mass number, they are different. Mass number is straight and forward. It's a number of protons plus a number of neutrons. But when we're talking about the atomic weight, you need to know the percentage composition of each isotopes. Percentage compositions need to be identified or given to you. Okay, say for example, when we are talking about carbon, let's say that carbon has two isotopes, which is carbon 12 and carbon 13. So the percentage composition of carbon 12 would be about 98.8%, and the percentage composition of carbon 13 would be about 1.2%. So these numbers would help us to calculate the average atomic weight of carbon, which means that we're going to multiply that with the mass number 12 times 0.988. Remember, when you change the percent into decimal number, you move the decimal point 2 units to the left, plus 13 times 0.012. So when we multiply 12 by 12 times 0.988, mathematically you may get, let me do my calculation, it might give you about 11.78, and when you multiply 13 by 0.012, if you do the calculation, it would give you around, let's see, 13 times 0.012, it gives you around 0.156. Now if you add them up, 11.78 plus 0.156, it gives you about 11.94 AMU. By the way, AMU is a unit that stands for measuring a smaller mass. It's called atomic mass unit. So 1 AMU approximately equals to 1.67 times 10 to the power of minus 24 grams. Again, AMU stands for atomic mass unit, which is used to measure smaller quantities, atomic mass units.